Now capacitors can be pretty confusing, but we can kind of think of them as a place to store charge. So we have capacitors here, and they're going to be measured in a unit of farad, which is essentially coulombs over volts. So we're trying to store charge within two equal potential lines. So I'm going to set them up right here. One here would be basically the positive one, and the other one would be the negative. So we would have the positive side here, and right now they're not going to even be charged up, but we're just going to sort of assume that that's where we would plug the positive side and that's where we would plug the negative side, because usually this is going to be hooked up to a battery. So we'll put the battery down here, and we would say, okay, this is going to be the 9-volt side, the plus side, and that's the minus side. But here we would have 9 volts, and here we would have 0 volts. And so because these are equal potential lines, this is going to have the same voltage, so we have 0. And then this is going to be 9 over here. So we can see how anything that's connected to this line is going to have 9 volts. It's just going to go right up there, unless it's going to have 0 volts. So it doesn't really matter. It's very important, though, that these kind of like don't touch each other, because otherwise, like, that wouldn't really do anything. You wouldn't have a capacitor at that point. You need to have space. You need to have distance. So once you have distance, then you start to build capacitance in there. Now, usually there's going to be like an electric field within this area, right? Because, you know, higher voltage points towards lower voltage, right? And so the electric field between two plates, I think we already know, is supposed to be like surface density divided by epsilon, right? Well, at first, let's assume that this battery is off. So we would have electric field being equal to 0 because there's no charge, all right? But let's say as soon as we turn on this battery and there becomes a voltage difference, then we could start to calculate voltage, because VF minus VI is going to be equal to negative the integral from 0 to x, since we're going to be using the x over here, and this is the x distance right here. But it's going to be whatever the electric field is, and then dx. And you're integrating the electric field over dx. Separation distance there. That's to find the voltage between here. And if the electric field is constant, then it's pretty simple, because then things simplifies down to V equals negative EX equals negative EX. And in fact, you could kind of find a voltage at any point here. So it doesn't have to be all the way to the end, but you can kind of find your way, like, I don't know, halfway through here, and you'll be able to calculate the voltage using those equations right there. The idea is, if the electric field is constant, you can just use that one. But if the electric field has an x in there as a variable, then you have to actually use the integral, because you're going to end up with an x squared divided by 2 kind of thing happening. But yeah, so now we can also calculate how much work would be done by moving across this. If a particle moves this direction, it does no work. Okay, that's important, because it's just moving along the equal potential surface. It's just going that way. But if it starts moving in this direction at all, you know, with or against the electric field, then you're going to get work equals to Q delta V. All right, and now we could start to look at this charge. This is actually a charge moving around here. Okay, and this is the surface charge. So that's why this is in purple, and then for the actual charge that's on the surface, I'm going to make those in green. This is just some random charge moving around there. But anyway, let's just say we have a Q. That's going to be the surface charge. And that's going to be equal to a constant C, that's the capacitance of the capacitor, times voltage. All right, so we have Q equals CV. This is a very important equation. Now let's imagine we turn on this battery. We start adding some charge to this, because now all of a sudden there is going to be a voltage difference. The thing is, you could try to keep cranking up this voltage. The capacitor is just going to be still. There's no, I'm just going to keep that in black so that you can see there's nothing going to happen there. But this one here is going to be possible to change. You can add bigger batteries, and that will be able to increase the charge. But at some point, the capacitor is just going to blow up. So there is a max voltage that you can hit. And because of that, you know, we want to be able to do some sneaky tricks to add more charge. But the idea is, you know, this side's going to have the plus charge plus Q, and this side should have the minus Q on that side. But you can kind of see this is kind of how the capacitors are built. And again, these are equipotential lines. Equipotential. And let's not forget how the electrons travel, because the electrons are going to be repelled by the negative. So they're going to want to move away from the negative in this direction at first. And then they're just going to follow this line, this direction, and then cross over there. And then they're going to come down here and enter the battery one more time through here. So this is the direction that the electrons will travel. And we've been talking about this capacitance, this C right here. Let's define what capacitance is. It's kind of like the body armor of these equipotential lines. So it's essentially like a property of that thing. You can't change the capacitance very easily. For parallel plates, you can have C equals, I'm going to put the K epsilon naught A divided by D. This is the distance of separation between here and there. The area is the area of the plate, epsilon naught. And the K may or may not be there, depending on whether there's a dielectric. I'm just kind of putting that there for now. You just ignore that. We're going to talk about dielectrics later. The idea is, you see is just going to be epsilon naught A over D, usually, unless there's a dielectric. But you can see how it's going to be pretty hard to change the capacitance. You can make it a bigger area, you can pull a bigger distance, or you can add something in between there to deal with. That's what the K would do. But this, you know, there's a few ways you can change the capacitance, but usually once you have a capacitor built, like, that's it, you know. You're just going to leave the capacitor. You're not going to try to stretch the capacitor unless it's a stretchy one that you can stretch around, right? I mean, you're not going to, like, try to, like, build the area bigger. How are you going to do that? I don't know. So it's a little harder. You can try to stick something in between the capacitor, but it's a little harder to mess around capacitance. So usually capacitance is pretty fixed, all right? That's almost always, it's like usually it's a given number too. So anyway, there's other types of capacitors, not just plates. Something like a cylindrical capacitor, and that would actually be something like our body. These are pretty common little capacitors. You might see them all over the place in like circuit boards and stuff like that. But 2 pi epsilon naught, and then the length of the capacitor, and then divided by ln, and then R2, this is the outer radius, and then R1 is the inner radius. So it's kind of like, it's like a tube or something, basically. And we also have spherical capacitors, which would be C equals 4 pi epsilon naught, and then we would have R1 minus R2, and this is going to be like the outer and inner radiuses. R2 is outer, R1 is inner, divided by R2 minus R1. And for an isolated sphere, we have C equals 4 pi epsilon naught times the radius. There's just some different capacitors and their capacitance. So I've drawn out some capacitors that are in series and some that are parallel to each other. Parallel, you can see that you can actually draw like a straight line through that with no breaks. It's just going to go right through. Over here, you can see how these are connected kind of like little stairs, but the idea is that we can't connect those two in series. Those are not in series. There's something branching off here, so we can't actually, this is a completely different thing. We can't add 1, 2, 3, 4 together and call that one, because then our calculations would be off of the entire thing. So we have to actually shrink this down into one that's over here first. You look at the parallel ones, put that into one capacitor, and then you can add in 1, 2, 3, and then 4, 5, 6 as one capacitor. But let's just say something was parallel. That would be these ones. Again, you just kind of draw like a dashed line through this, right? But C EQ, that's going to be, if I combine these into one, the equivalent capacitor is going to be the sum of the charges, charge 4 plus charge 5 plus charge 6, divided by all under the same voltage. They're all going to have the same voltage. The idea is that over here you can add them just simply C4 plus C5 plus C6. And there you go. 4, 5, and 6 together would just be, if this had a capacitance of 4, and then 5, and then a 6, you add them together, and that would be 15. Bam. And so your equal capacitor, if you had just one here, if you shrunk it all down to just one, then you could call that 15. And you could have C1, 2, 3, and then capacitance of 15 right there. So that would be like parallel. But if we were in series, this other one right here, then you would have to say 1 over CEQ. That's going to be the reciprocal. But here, you're going to sum up all the voltages. And then you're going to get your charge at the bottom. This is going to be all the same charges. They all have the same charge. And so, again, that's kind of why you couldn't really add this one in until you added all those up together. So that way you actually had that final charge that you could add into that. So we have 1 plus 1 plus 1. This is how we add up, all divided by their capacitance, C2 and C3. So like if we're trying to add these series up, remember I said 1 over 1, and then 1 over 2, and 1 over 3. And if we add up the final one, 1 over 15, that would be how you can add things up in series. Now, for the battery section over here, just keeping in mind, hey, we got 9 volts, we got 0 volts, and this should connect up over here, 0 volts over here. And you want to be kind of careful, because if you start noticing that, like, all of a sudden these lines connected and there was no capacitor here and it's connected to the other side, then like that would be weird, because then you'd have 0 volts on both sides. So you have to actually connect. Every time you draw one of these circuits, try to actually connect these voltage points. Trace it from here. 9V goes over here and then it stops. And that's it. We don't know what these ones are in the middle. That's why we have to calculate these in this very specific way. This is crazy. Now, dielectrics are pretty common ways to change capacitors, because it's pretty easy to just stick something inside your capacitor. Like you could just take a can of soda and just put water into it, and that would increase the capacitance because now you got stuff in it. The idea is that you have the permittivity of free space, and you're gonna add a dielectric to that. You're gonna take empty space and stick something in it. That's what K is. So that's when we have, anytime there's an empty space in this, we could stick a K there. Alright? And that's what the dielectrics do. Now you can actually stick 2 different dielectric materials into something, which makes it slightly more complicated. But you could put them in series, which would be something like this, K1 and then K2. You can see how they're lined up kind of like this, separated. So it looks like this in series. You could do that, or in parallel it would look like this, K1 and K2, and you can kind of see how they're sort of separated like that, and so it's kind of just like right across like that. But the point of these dielectrics, the reason why we want to put them in there is because they will increase maximum voltage. It would also reduce the electric field. And so that's kind of the main point of these capacitors, and the dielectrics. In fact, this is the main point, really. Because it reduces the electric field, that allows the voltage to be increased. So those are the byproducts of the dielectrics. So there are 2 kinds of dielectrics, one that might be polar and one that might be nonpolar. So polar atoms already have their electrons like really far apart and stuff, and so they've got a dipole within these atoms. So they kind of already have a big plus and minus separation within those atoms. So if there's an electric field around, they're just going to instantly like snap to the field, and they're going to be kind of wide and just really make big arrows and stuff here. But they're going to counter the electric field because look, the negatives are going to be attracted to the positive, and the positives are going to be attracted to the negative. And so then within them, you're actually going to get a smaller electric field that goes counter that direction. Now they're not going to align exactly up, but they're going to be really, really close. So they're going to create a very strong electric field against the electric field that's already in there. So that's why these things will have a very high K, and they're going to be able to reduce the electric field quite a bit because they have a high K. Now the nonpolar dielectrics, these things are going to kind of start out like that. If there's no field, there's just going to be pretty much, there's no polarness to these to the atoms inside. So as soon as you turn on the electric field, you might create an induced charge inside of those atoms, and so that'll kind of like create a smaller electric field within there. So you just have like these little arrows that are kind of countering here. So nonpolar dielectrics are not really quite as good at countering the electric field. So you can see that if the alignment is better, if you have a better alignment, meaning the atoms inside are polar, then yeah, they're going to line up better, and so you're going to have a higher K. And because these nonpolar ones don't line up very well, they're going to have a low K. And that's just a general rule, but that's kind of how this works. Now we can return to the math over here, and we can state that E equals E naught over K. So the original electric field that you had in there, as soon as you add a dielectric inside, it's going to create a new electric field that's going to be weaker. But the capacitance is going to increase KCO. This is the C naught, that's going to be the initial one. So you can actually look back up here to our original equation. If it was just, if we took away the K here, then you can see it's E naught A divided by D. But as soon as you add the dielectric inside, then you get a K right there. Now remember the induced charge that we were talking about over here? I believe that these would be called QI, the little induced charge that's right in there. It turns out that we have a little equation for that as well. QI equals Q1 minus 1 over K, and that's going to be the induced charge. And then the energy stored, the potential energy, U, if you want to store energy inside of a capacitor, well, it's also going to be K, U naught. So similar to what the capacitance does, it's just going to increase the energy stored. Energy stored. The idea is that if you have a high K, it's a really good dielectric, so you can have a high energy storage, a high Q storage. This is good for like power supply, right? Power supply. But if you have a low K, then this would be kind of a bad dielectric. You only get a very low Q storage. But this is fine for things like circuit boards, because those are really delicate, and so you don't really want to break them. Low Q. Now let's discuss this potential energy stored. Potential energy stored. That would be U equals Q squared, and that's going to be the Q that's on the charge, on the capacitor, divided by 2 times the capacitance. That's kind of usually the given number there, so that's why it's in black. And then we have the C, another equation for this energy. If you know voltage, you can use this equation, CV squared divided by 2. If you know the charge, you can use that equation. And there's another equation called energy density. That would be something like a fancy U is epsilon naught, and then the electric field squared divided by 2. or you could say the regular potential energy divided by the volume. And so you can kind of see that energy density is really the joules divided by the volume, m to the third. Volume tends to be area times the distance. This is within the two metal plates, right? So you would have like the d and the area, and that would give you like a volume, right? So this is the distance of separation, this is the area. You can see how that would create a little bit of a volume there, and you could put a certain amount of potential energy, which is that stuff, which comes from, over there. Just stick that in there, and you got a really energy density. So yeah, this is basically everything about capacitors that I know for now. And next is going to be resistors.